Hello boys and girls! In today's episode of Mastering Factorio, we'll take a practical look at circuit networks. We'll cover common input signals, the core components, and a few useful applications. This is not a complete guide. The goal is to focus on things you will actually use, not on wiring yourself into a philosophical debate about logic. Let's start with the components. First, there are the wires, red and green. They transmit signals and do not mix. A signal on the red wire stays on the red wire no matter how much you wish otherwise. Circuit wires are connected through power poles similar to power cables. Next is the constant combinator. It lets us define fixed signals. This is usually where things start to feel real. Every item, recipe, letter, and several special icons can act as signals. Each signal has a strength or a numeric value. These values are always whole numbers, which will matter later. Then there is the decider combinator. It evaluates conditions. It compares input signals using operations like equal, greater than or less than, and outputs a signal if the condition is met. This is where factories start making decisions, for better or worse. Closely related is the arithmetic combinator. It performs math on signals. As mentioned before, everything uses whole numbers. Fractions are not welcome here. New in Factorio 2.0 is the selector combinator. It allows us to choose one signal from several based on a criterion. This turns out to be surprisingly powerful once you stop fighting it. Now let's look at input signals. Containers are the most basic source. Chests and tanks output their contents. When multiple containers are connected, their signals are combined. Different items appear as separate signals. Identical items are added together automatically, and you can save yourself the arithmetic combinator to do the job. Roboports provide information about the logistic network. We can read available items as well as the number of construction and logistic robots, which is useful if you want your factory to quietly fix itself. Power-related entities are also useful. Nuclear reactors output their temperature and accumulators report their charge level. Both are excellent indicators of how close you are to a bad decision. Train stations are where things get interesting. From a station, we can read the contents of a stopped train along with other train-related data. This is where circuits start influencing logistics instead of just observing them. Belts are another powerful input source. You can read them as pulses, as a single segment, or as an entire belt. Pulses exist, but you will rarely need them. Belt segments are separated by splitters, but multiple segments can be combined to get the total item count. Finally, the output of any combinator can be used as an input elsewhere, which is how small, harmless circuits turn into scary systems. Rather than listing every possible application, it's more useful to look at a few real examples that combine these signals. These patterns are reusable, which is the whole point. One of the first uses you will encounter is controlling lubricant production. You usually want lubricant to take priority over cracking heavy oil. We do this by wiring a pump to a tank. That tank can be either the lubricant output or the heavy oil input. If multiple tanks are connected, wiring a single one is enough because fluids behave better than most other systems in Factorio. Nuclear reactors can be controlled in a similar way. One option is to check steam levels and only insert a fuel cell when they drop. Another is to read reactor temperatures directly. While reactors need to run above 500 degrees Celsius, heat takes time to spread. In my experience, inserting fuel at around 510 to 520 degrees Celsius works well and avoids a lot of unnecessary excitement. Robot production is another good candidate. If robots are built locally, we can check the X and C signals to keep enough construction and logistic robots available. We could also read the contents of the logistic network, including buffer chests, and use that to control production. If this already feels like something you might want to reuse across multiple factories, that's a good sign. And if you want more of these reusable patterns in future episodes, that's a good moment to like and subscribe. Not because it helps me, but because it tells me this level of detail is worth continuing. Train signals are most powerful when combined with dynamic routing and interrupts. We won't go deep into that here. You can disable stations, limit trains, or assign priorities. Priority is usually the most useful. The other options tend to create trains that wait very patiently in the wrong place. By combining priorities with waiting bays, we can control exactly where trains go. They can be sent to the station with the most material available or the one that needs it most. For liquids, this is straightforward. 4 tanks hold 100,000 liters. Dividing by 1000 gives a value between 0 and 100, which works well as a priority signal. Often this is only needed on the loading side. For unloading, we invert the signal by multiplying it by -1 and then add 100. Full stacks become low priority, empty tanks become high priority, and the trains behave. When I first turned this into a reusable circuit blueprint, I was justifiably proud of it. For solid items in chests, things are more complex. Stack sizes matter. Let M be the maximum capacity as the stack size, N the current item count, and P the resulting priority from 0 to 100. Once this works for loading stations, the same logic applies to unloading with the addition discussed previously. We calculate M from the number of chest slots. For a 2-wagon train with double-sided loading, that's 1152 slots. Single-sided loading halves that. Multiplying by the stack size gives the maximum capacity. The current item count is read directly. Because we have only whole numbers, dividing n by m would give us either 0 or 1. To fix this, we multiply n by 100 before dividing. This produces a usable priority value and avoids disappointment. This setup can easily be turned into a blueprint and parameterized by item. Belt reading is useful in many situations, but it shines on space platforms. Excess items often need to be discarded. For processed items, we check belts further upstream and throw items away once they back up. For asteroid chunks, reading the entire belt loop gives a much better balance. There is also a simple way to void liquids. This is especially useful on a qual where liquid imbalance can block production. We pump liquid from a tank into a machine, usually a chemical plant, with the pump controlled by the tank level. We define 2 recipes in a constant combinator, one that consumes the liquid and one that does not. These go into a selector combinator set to random. When the recipe switches, any fluid inside the machine is destroyed. This feels wrong, but it works. Finally, let's build one more circuit together. In space, chunk availability varies, while demand stays mostly constant. Since chunks can be converted, we can balance production with logic. We read the entire ring belt and combine all segments. Our goal is to identify the chunk type we have the most of. We eliminate the chunk with the lowest amount, then compare the remaining two. This isn't the most compact solution, but it's easier to follow. We compare pairs and output values only when the left-hand chunk is larger. This removes one chunk type. We then split the signal into 3 branches and enable only the branch if its chunk was eliminated earlier. In the final step, the remaining 2 chunks are compared and the larger one outputs a value of 1. We combine the item signal with the enable flag using a red wire to prevent interference. At the end, only one branch remains active. Wiring the outputs together gives exactly one chunk signal, the surplus. Now that we have seen the over-engineered solution, which showcases everything we have discussed so far, let me present the simple solution. We use a selector combinator and select the first input with descending sorting. This gives us the maximum chunk count. Instead of outputting the chunk, we output the corresponding recipe and feed it into the crusher. Another useful application on space platforms is speed control. Fuel can be stockpiled during stops, so production does not need to match consumption perfectly. But higher speeds can overwhelm defenses. To avoid this, we limit speed by only pumping fuel into engines when velocity drops below a chosen threshold. If you have questions or want to see different applications, let me know down in the comments. That's it for circuit networks. Next up, we will look at quality modules introduced with the space age expansion. Until then, see ya!